let's try this a little bit longer. Okay, so guys, give me any vector you want right here. Say again? Like that? Perfect, okay. Great, so T of that is going to be the matrix 1, 1, 1, 1. Okay, great. Somebody give me another vector over here. Just make sure it's not a multiple of this one because we need these two vectors to be Li. So somebody give me another answer over here.
0, 1, 0, 3, 0.
Like that?
Yeah.
Okay, great. So these are definitely Li. Now, when we transform those vectors, what will we get? Well, we're going to get, for the first one, we're going to get 1, 1, 1, 1. And for the second one, we're going to get 0, 1, 0, 3. Oh, shoot. I was hoping that the two answers would become LD. That was what we were supposed to be showing, right? A counterexample. So these are not LD, so I need somebody to change, I need somebody to fit. This is the way you're going to find it when you take the exam. You're going to try something, and it might not work the first time. So we're going to have to play with it a little bit. So what would you change to make it work?
So you said you want a vector that's not a multiple of the other, but you want it to be linearly.
I want the result over here to be linearly dependent on this one. So let's just change the second vector. Jennifer?
Can I do 2, 2, 2, 2, 0?
2, 2, 2, 2, 0. I love it. 2, 2, 2, 2, and 0, right? Those two are not multiples of each other because of the last slot, right? However, the outputs of the transformation are multiples of each other, and so now that is LD. Okay? And there's 1,000 other answers you could have given instead, but that one certainly works. Does that make sense? So just, part of why I'm doing that is to just remind you that, one of the things I'm probably going to ask you to do on Tuesday is give me an example of something, here or there. I don't even think I'm going to write anything else down on this. I'm just going to kind of leave it at that, because that's basically the point I was trying to make. Okay, it is 4. However, I was going to maybe do one more problem. Can I do that? If you have to go, it's totally fine, of course. But I was thinking of maybe doing one more problem. Should I do that? Here. The thing is that, I used to do these review sessions that would just go on and on and on. Nobody would leave. Because they're like, oh, the next thing he does is going to be like the thing that's going to be on the test. I finally realized that I actually need to just stop doing the problems, because otherwise we're just going to stay here for the next 8 hours. So I'm just going to do one more, and then, I feel pretty good about the stuff we've covered, but I didn't really talk about chapter 2. And I think I should do something from chapter 2. Okay, so let's do one more example. One more example. So let's do this one. This is number 6. So I'm going to let V equal W equal P3 of R. And I'm going to define T from V to W via T of A plus Bx plus Cx squared plus Dx cubed is going to be equal to 3a plus 6d plus negative a plus b plus cx plus negative c plus d times x squared, and then plus negative b minus 5c plus 2d times x cubed. Okay. So what I want to do with this is a few parts, okay? The first part is I would like to find a basis for the range of t. We're just going to do about 3 or 4 parts. Probably take us maybe 15 minutes to just try to finish one last example. Okay. Let's try to find a basis for the range of t. Okay. So we didn't review the range of t, so I wanted to remind you about that, right? The range of t. You guys remember the range of t? How that works?
The span of T1, T2 to Tn, where we want to be in the other bases that we.
Exactly right. We're just going to take the span of the transformation of, how many vectors will I have for the basis for v?
4.
Right, P3 of R, right, is 4-dimensional. So I'm going to write this as T of V1, T of V2, T of V3, T of V4. But then, can somebody suggest, what is a nice basis that you're familiar with for P3 of R?
1x squared.
1x, x squared, and x cubed, right? This would be like a nice basis to work with. It's not the only choice. You can use any basis that you want. But this is a nice one to work with. So let's try and work with that. Okay. So let's start working this out. What is t of 1? Like, how do we figure out what t of 1 is? We have our formula. This is a pretty big, messy formula, but this is what we have to work with. Okay. So if I want to know what t of 1 is, that means I'm going to put a 1 where I see the a variable and 0 for the b, c, and d variable. So if I do that, I put 1 for a, I'm going to get 3 right here minus x, and that's actually it because there's no more a's other than that. So 3 minus x would be the first one. Okay. Now to figure out t of x, I'm going to put a 1 for the b variable and a 0 for everything else. So where is my b over here? Right here I have a b, so this is going to give me x, and then over here I have another b with a minus, so minus x cubed. So x minus x cubed. Okay. Then the third one, t of x squared, for that I'm going to put a 1 for c, and it looks like I'm going to get x minus x squared minus 5x cubed. Okay. And then finally, when I put a 1 for the d variable, I'm going to get 6 plus x squared plus 2x cubed. Let me know if anybody doesn't know how I got those results, that this is a good time to ask me. So I'm just putting in the 1 for the a, b, c, and d kind of separately. Okay? So is that my basis for the range of t? Exactly. I have to check if these 4 polynomials are linearly independent. They are definitely going to span the R of t. That's a good thing because R of t is the span of those vectors, right? So there's nothing to worry about with that. But the Li is the issue. So if you remember, we just did a theoretical linear independence problem where we had to use the definition carefully to write it up. This is much more like cookbook, put it in a matrix and do your steps to it. So I'm just going to put it into a matrix. When you're putting these vectors into the matrix, they always go in the columns. The first vector is basically a 3, and then a -1, and then a 0, and a 0. So don't forget that there's actually 4 different powers of x there. Right? Constant term, x squared term, and x cubed term. And let's just do that for each of my polynomials. So the next one has no constant term, a 1 on the x term, and a -1 on the x cubed term. The next one has no constant term, but it has a 1 on the x term, a -1 on the x squared term, and a -5 on the x cubed term. And the last one has a 6 up here, and then a 0, and a 1, and a 2. And for linear independence, you take this system and you augment it with all zeros. So what I'm doing here, guys, is I am checking Li. Yeah.
Could you please explain why we need to use it in columns and not?
That's a whole big write-up about, basically what it is if you just set up a linear system of equations, so if you just set up these polynomials into a system of equations and set it equal to 0, then if you just look at what the constant terms are, right? So you have a 3a, and then you're going to get a 6d. The constant term has to equal 0. Well, this one here, this is my fourth polynomial. I just put a dot, dot, dot right here. But eventually you're going to get a d times 6.
All the constants at the top, I see.
Right, so all the constants, I'm sort of grouping them together, right? So the 3a and the 6d, that makes an equation.
Okay.
And that actually gets reflected in the first row of this matrix now. And then the x coefficient, there's a negative a and a plus b, right? And a plus c. So that's the second row. Okay, so usually the first time I ever show this to somebody, I would write the whole thing out and then put it into the matrix. But after, we've done these for like 2 different linear algebra classes by now, probably you always see that this is what's happening. Your polynomials go into the columns like this, and then if you look at it row-wise, you have all of the constant terms right there in the first row, the x terms are there, the x squared terms are there, and the x cubed terms are there. Of course you can switch these rows. You don't have to start with the constants on the top row, but this is what you're going to get. Okay, so what we have to do is we have to row reduce this and see what we actually come up with. And let me just do that kind of quickly here. The first row, I'm just going to divide it by 3 to get a 1 in the upper left corner. And then I'm going to add that row to the second row. Okay, I'm going to go fast on this because this is the boring part. Okay, so I just divided the first row by 3. And then I'm going to add that to the second row in order to get a 0 here. Right? So then I'll get a 0, a 1, and a 2, and a 0. Okay? And then the third row is already 0, 0, negative 1, 1, 0, and the fourth row is 0, negative 1, negative 5, 2, and 0. Now let me add the second row to the fourth row. You guys can do the EROs quickly on the exam as well. Like back when you probably first learned them in your very first linear algebra class, they were very picky with you. Do one step at a time, explain what ERO you're doing. Right? We can kind of jump a little quicker at this point. This is kind of the easy stuff. And again, if you make a mistake on this, right, it might give you the wrong answer, but I won't be, docking tons of points, and I'll follow your calculations through to see what, your results would give you. Okay, if I add the second row to the fourth row, I'm going to get a negative 4, and a 4, and a 0. And now I can actually see that the fourth row is a multiple of the third row. One thing that is really a good idea to do always is to circle your pivots. So what is our conclusion here? Are these vectors Li? There is a free variable right here. There's an unpivoted column in the row echelon form of the matrix. And what you have to do, therefore, to find your basis is, okay, so we've decided that these vectors are LD. Please do not just throw a vector away randomly. The example I always like to give is, I saw a student do this once. The student looked at these 3 vectors, and they said, these are LD, so I better throw a vector away, and they threw this one away. And they left themselves with the linear dependency is still there, right? So we have to be a little bit cautious how we do this. The way to get it right is to just notice that the unpivoted column is the thing that's the problem, right? If we didn't have the fourth column, now we would have no free variables, and so we would have Li set. So, all right, let's get rid of that column. Just trace back through your work. What does that really mean? If I'm getting rid of this column right here, doesn't it just mean that I'm actually getting rid of this vector right here? It's the fourth column coincides with the fourth vector. So your basis then, the answer to this question is just the first three polynomials there. Okay, it's going to be just the first three. Okay. Everybody good with that? Let me give you a part B if you're good with that. Okay. I'm going kind of quickly, but this is actually this could be a 250B question as well, but I've got a couple more parts here to be a little bit more interesting. Can I erase my EROs? Everybody good if I erase this part? Okay. Here's part B. Okay, I want you guys to put on your thinking caps for this. Part B. Part B, ready? Prove that the set -2 minus 3x plus x squared plus x cubed is a basis for n of t. This is a great problem. This is a great problem. Because it's quick. It's quick. Okay, n of t, that's the vectors that get killed by the transformation. So this is a pretty kind of weird polynomial to just come up with, but I'm giving it to you and I'm saying, show that it's a basis for the null space. So what might you want me to do here?
Maybe plug it and use the transformation, see if we can do one.
Okay, let's transform the vector that we were given and see if it gets killed. We at least should find out if this is even in the null space. If it's going to be a basis for the null space, it better be part of that null space. Let's just transform it, right? So this is the first step. This is not the whole solution, but this is the first step, is to just work this out. What is t of that? Well, that means I've got to put -2, so a is going to be -2, b is going to be -3, c is going to be 1, and d is going to be 1. If I take those numbers and I plug them here, -2 for a and a 1 for d, that gives me 0, plus -a plus b plus c, that's 2 minus 3 plus 1, that's also 0, right? And you just keep going like that. -c plus d, that's 0. And finally, -b, which would be 3 minus 5 plus 2, that's also 0. Okay, great. So this is the 0 vector. And that's what n of t is, right? It's those vectors that get transformed to 0. So we can say that -2 minus 3x plus x squared plus x cubed is definitely in n of t. So now, why is it a basis for n of t? A single vector by itself is certainly Li. I would agree with that. That's half of what it takes to be a basis, right? A basis has to be Li and has to span the space. A single vector is definitely Li. So let me just point that out. Note that this set, -2 minus 3x plus x squared plus x cubed is Li. Clearly, you guys can say that too on the test if something is obvious. But hopefully it'll be obvious to me as well. A single vector is always Li unless it's the 0 vector. The 0 vector, of course, is an exception to that. But so how do I know it's going to be a spanning set? How do I know it's actually a basis? what we're really saying is that everything in the kernel, everything in the null space has to be just a scalar multiple of that. Now, how do I know that without like checking everything? I could set this equal to 0, 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 and create a system of equations and solve for A, B, C, and D, and find out that, yeah, every possible choice of A, B, C, and D that works is a scalar multiple of this one. I could do that. That's the hard way. I want the fast way. And it's a very, very important theorem.
Can you just plug in A, B, C, and D there in your...
In the transformation? Yeah. Well, that's what I did with these numbers. Right, and I got 0. Right.
Use the rank notated there?
Say it louder.
Use the rank notated there?
That's the one. We haven't talked about that in 2 hours, and I should have done that sooner probably. The rank nullity theorem, right? What does that say again? Let's just write it down here. Rank nullity is that I actually called it I think I referred to it as the general dimension theorem, right? So the dimension of V, right, it's the nullity or the dimension of N of T plus the dimension of R of T, right? And we already showed in part A, what was the dimension of R of T? It's 3, right? So this one is a 3 plus whatever this number is has to equal, what's the dimension of V? 4. So my nullity is one-dimensional, and I found one vector in it. So that's your basis. Isn't that clever? So you don't actually have to find the whole null space directly. You can just simply say, here's one vector that's in the null space, and that has to be a basis for the whole entire null space. Okay, so let me just point that out. From the dimension theorem, the dimension of n of t is equal to 4 minus 3, which is equal to 1. So it's one-dimensional, and so the set -2 minus 3x plus x squared plus x cubed is definitely a basis. It's the right number of vectors. It's one vector, and it is also a linearly independent set. So therefore, it's a basis. Okay, just 2 more quick things here. I promise we're almost done.
Can we skip the part where it says where you say clearly one vector is linearly independent? Like, we don't say that.
That's odd because it's so clear. Yeah, you wouldn't need. This is kind of optional to say that. I'm just trying to be thorough. Yeah, that's right. Okay, so let me ask you one more thing. Actually, 2 more things, really quick, then we're done. And guys, I'm not reviewing absolutely everything, right? Okay, this is just to give you an idea of a taste of some of the stuff. So, part C here, guys. If beta is equal to x squared, comma 1, comma x cubed, comma x, find the matrix representation of T with respect to beta. So this is more recent material. This is a matrix representation. And of course, when I write it like that, I have to remember that because T is going from V to itself, right, the V and the W are the same, this is really like having the same basis on the top and the bottom. I kind of like to add that, but it isn't always provided when you read the questions in the book. So this is the matrix representation. Okay? Let's see if we can do that. So what size matrix am I going to be expecting here? Yep, we've got a 4-dimensional space mapping to a 4-dimensional space. Remember that normally the size of this matrix is it's the dimension of W by the dimension of V. So there's W rows and V columns. And how we get this matrix is we just go column by column, filling in the columns with the transformation. So what we have to do is we have to transform these vectors. I have to transform x squared, and then write that in terms of beta. Then I have to transform 1, write that in terms of beta, and so on. And I have to do this in the correct order. I kind of put these out of order for a reason, just to make sure you're being careful with that. Right? Okay, so t of x squared, let's just figure out what that is over here. What is t of x squared? Well, that's where c is equal to 1 and everything else is equal to 0. So I think we did this before, actually. It should just be x minus x squared minus 5x cubed. Right? And now I have to write the coordinate vector of that relative to beta. So I'm going to write a column here. The coordinate vector for this guy, right? So what would that be actually?
0, 1. Well, actually, sorry.
We got to use the ordered basis over there. This is the trick, right? We got to go back and put them in this order. So the x squared number has to come first.
So
Negative 1, then
0.
0, then
Negative 5.
-5, and then 1. Exactly. Okay, great. So that goes right here. -1, 0, -5, and 1. Okay? Now we go to the next vector, and we do the same thing. So actually, I'll come over here. You guys can try and work it out while I'm erasing here. See if you can figure out what t of 1 is, and then what the coordinate vector for that would be. And then we'll write it down. Okay, what is t of 1?
3 minus x.
3 minus x, that's right. Okay? And so if we take that result and write it in terms of beta again as a column vector, right? So in terms of this basis, right? Everybody see what I'm doing? I'm going to write 3 minus x in terms of this basis. So how many x squareds do we have? 0. How many multiples of 1 do we have? 3. How many x cubes? 0. And how many x's? -1, right? So we're going to get 0, 3, 0, -1. And that would then be the second column of this matrix. 0, 3, 0, and -1. Okay? Does that make sense? All right. Next I have to do t of, what's the next one? X cubed. What is t of x cubed? T of x cubed, according to my formula, 6 plus x squared
2x cubed.
plus 2x cubed. Great. Okay, so we've got that. So let's put down the coordinate vector of that relative to, what's this, beta. Relative to beta here. So I have to start with the x squared term. There's one of those. My constant term is a 6. My x cubed term is a 2. And there's no x term, so I get a 0. So the third column here is 1, 6, 2, 0. Right? Finally, I have to do t of x. I'm almost done, guys. So t of x is going to be, if I put b equal to 1, I'm going to get x minus x cubed. Okay? So if I write down that coordinate vector relative to beta, I've got to put x squared first. That's 0. Constant term is also 0. The x cubed term is -1, and the x term is 1. So we get 0, 0, -1, and 1. Okay? Is everybody understanding this? How I'm getting this? It's very computational, but it's also, this is of all the stuff we've learned in this semester, this is probably like the newest, freshest material. I mean, it's the stuff you probably haven't seen before. So.